Okay, so before, go ahead. I don't give out my quiz questions because if I do, then the next semester people have the quiz questions and don't get this experience. So I consider the quiz a conversation and you need to be present for the conversation. Go ahead.
Are we going to have a quiz on the chapter 7?
I don't know if we have time. We'll see. It would be nice if we could, but sometimes what I do when we run out of time and I need it for lecture is I post a little online practice quiz for you guys, which I could do for this material. Okay, so let's talk about your, you are always welcome to write the quiz questions down, by the way. So I don't want you taking photos of them, but you can write them down. Typically speaking, because if people take photos, they feel free to disseminate digital information. And I don't want it out there for the next semester. And it's not just because I'm a bastard, it's because I need people to engage in the process real time and not memorize the answers. So that's not what they need to do. So you can write down the questions as much as you want to. By the way, I know that most of you guys won't take me up on this and some of you can't. But today is the day that things start getting deep with Biz and a little different than you have done in other classes. Because a lot of stuff we've talked about, you've like touched on it and just applying it in a different way, and we did in other classes. So you are invited and welcome to come to the 8:30 class if you want to. You can sit through both of them. He sometimes sits through both classes. Sitting through the class twice is almost like 3 hours of studying. It's like, oh yeah, I totally have it now because you hear it twice. First time it's just exposure, and then second time you're like, yeah. Oh, and Jacoby does too quite often. He sits back there. Okay. It's kind of a really efficient way of studying. So let's talk about your test. Your test, I assume, is going to be a week from today. Today, Thursday? Yeah? So we're just going to keep it that way. If, by chance, we didn't finish the material, and I'm pretty sure we will, then what would happen is the material would just roll over to the second test. Just that's all I do. So we're going to keep the test date on Thursday. So what do you expect about tests? Wait. You asked a question, I forgot what it was.
Yeah, I wanted to know what your style was like.
Okay, so let's talk about that. There are a couple of people who've had me before. You've had me before, and you have, and Caroline, and these guys, a bunch of you. Raise your hand if you've had me before. Okay, whoa. So ask them when I leave, because I'll tell you how I think they are, and then they'll tell you how they think they are. I don't take my tests. I write them, and I know all the damn answers, and they seem completely obvious to me. They are multiple choice, and then there is always a written component. And the written component on the first test is not going to be really essay intensive because I want you to do an essay as a bonus first. And then let me give you feedback on how that was graded. And then on the second test, you will have like real essays on the second, third, and fourth tests. So there will always be written labeling or something, and this one you know one of the questions, right? I told you that the unbalanced summary equation and the significance of cellular respiration are going to be on the test. There'll be some other stuff that you have to write. My philosophy on writing on tests is that you should not get an A if you can't do demonstrative knowledge instead of just recognition knowledge, right? So A students need to be able to put it on a piece of paper out of their own brain, okay? So what happens, I think on this first test, I would imagine that it's probably 30% written and 70% multiple choice and true false, okay? And on future tests, it moves closer toward 50% as you guys get a little more confident with writing. So that's how. As far as if this is easy, you're prepared for, if that's easy, you're probably doing very well at preparing toward your test. Although the quiz questions, yeah, what do you guys think who've had me before? The quiz questions are a pretty decent indication of the level of testing. Yeah, not necessarily the nature of testing, because sometimes you have to write it down, but like, I think it's a pretty good indication. I try to make it. And how do you study? You study notes, and then you augment it with your textbook if you need to, right? So notes first, and then, or there are figures and things that you need from your textbook. So if you study it the other way around, if you study a textbook and then notes, you won't get the emphasis that I was trying to make. So your textbook is broader and deeper in some places than I want it to be, and not as deep in other places. So that's why I wrote the notes, just because that's what I am going to talk about. Okay, any other questions about your test? Everybody good? So yeah, feel free to talk to each other. The people who had me for anatomy, I test very similarly in physiology. Go ahead.
So do we need...
No, I'll bring them for you. Yeah. You're paying for something, right?
So no number 2 pencil needed?
Yeah, you need a pencil. Don't write in a pen on a Scantron. People still do that every semester. I'm like, oh, you're new, right? Okay, so we are going to start sort of where we left off last time. So we're going to start on the next set of notes, but we're going to start by building the same thing that we did last time, and then we're really going to change it dramatically today. So I'm going to build that whole cell in homeostasis, but I want you guys to help me. And then this is the other thing. You need to ask a question if you get confused, because I'm going to use this as a framework to start changing things massively. And if you don't understand the framework, then you're going to get really lost when I start changing it. So ask as many questions as you want. Stop me if you want to. Try to figure out why. I'll have you guys explain some of the whys as well. So basically we're going to start and we're going to rebuild what we built before, and we're going to add details to it. So we're going to start with the ECF and the ICF. And you guys are going to tell me that you already know. Yeah, I am. You guys are...
I can't see the little thing.
It's
Yeah.
up there. It was there before you.
Okay, yeah. You guys are going to tell me how to start. So in order to tell this whole story, all I really have to know is intracellular concentration and extracellular concentrations of sodium and potassium. So somebody tell me the ratios for potassium. Where is it high, where is it low, and then we'll add in the numbers. Higher where? Right here? Yeah, okay. Because you guys were all just saying BOSCF. I was like, what are you saying? Low here? Yeah, and from Texas, ICF sounds very similar to ECF. Okay, so what's the ratio? 30 to 1. Okay, there's nothing magical about that. That's just homeostatic for cells. Okay, that's just how it is if you measure it. And then for sodium, where's it high? ECF. Okay, ECF. And low here. And give me numbers. Okay, 15 to 1. Okay, there's nothing magical about that. Everybody understand it? Okay, that is homeostatic for cell. If you ever change it, you're going to eventually put it back there. It changes relatively frequently, but it's going to be a starting point. So what I'm going to tell is like a little bit of a fib. I'm going to tell you a story about the birth of the cell, but I'm going to separate it into like little distinct events, but really it all happens simultaneously. So it's really hard to understand what the hell is going on if you say 72 things happen and then it turns out this way. So we're going to do it sequentially, and we're going to start out with just this, okay? And what we're trying to get to is steady state or homeostasis for the cell, which eventually we are going to call resting membrane potential. And all we need to do is to start here, okay? And then I'm going to do the things that I did last time. I am going to initially just add in leak channels, and this one's going to be a sodium leak channel. And this one's going to be a potassium leak channel. And I'm going to tell you one other important thing before we start moving anything. At the birth of the cell, right before anything starts moving, I want you to note that the intracellular fluid is electrically neutral. For every positive, there is a negative. The primary source of negatives in the intracellular fluid is that there's a whole bunch of negatively charged proteins. And they're impermeable. You don't move proteins in and out of the cell on accident, right? They're structural and functional proteins. So for all practical purposes, they're going to be trapped inside the cell, okay? So large negatively charged proteins. So what I'm saying is in the ICF, there are as many negatives as positives before we start moving anything. And in the extracellular fluid, the primary source of negatives is a high concentration of the chloride ion. And there's other negatives out there too, but that's the one we're going to keep track on. And in the extracellular fluid, again, at time 0, before you start moving anything, it's electrically neutral. So for every positive, there's a negative, right? So now, neutral, neutral, stick it in my channels, start moving things, okay? You already know, but tell me again, which direction is sodium going to move? Okay. And which direction is potassium going to move? Okay. And at the birth of the cell, you only had to deal with concentration gradients, right? Okay. But then very quickly, you're going to end up dealing with charges because these ions do not move at the same rate. Do you agree? So initially, before you have any charge, which ion is going to move more quickly? Initially, before you have a charge, so potassium is going to move more quickly, right? So potassium is going to move out more quickly than sodium is going to move in. Does everybody understand why that is? Because before you have a charge, all you're dealing with is concentration gradients, right? Okay, so give that a second to occur. This is still all instantaneous at the life of the cell. And then what are you going to very quickly accumulate? What kind of charge is going to accumulate on the outside of the cell? Yeah, you're going to accumulate a positive charge on the outside of the cell. You're going to get really tired of drawing them. Okay? And then what's going to happen on the inside of the cell? You're going to get a negative charge. But can anybody explain to me in your words, because I did it last time in my words, where the negative comes from?
Yeah, so we had the same question that we were trying to sort out the other day, and now it makes sense that because potassium is leaving so much faster than sodium can replace it.
Yes, exactly.
That's what's giving it.
So am I actually accumulating negatives or am I revealing negatives? I'm just revealing negatives that were already there, right? Okay. So what I just did is just moved positives, but I didn't move them in equal rates, right? I moved more positives out than I moved positives in. And I revealed primarily those negatively charged proteins on the inside of the cell. Does that make sense? Okay. So it's not magic. Started out neutral and then you moved positives unequally. Okay, so now what's going to happen is now for the rest of the life of the cell, and this was really just the instant of the birth of the cell. For the rest of the life of the cell, this is how the cell exists, or we'll get back to immediately. Okay, so this is homeostatic for the cell. These concentrations need to be maintained or replaced here, and then this needs to be maintained or replaced. So one conceptual thing for you, just so you know, before we get into anything else. This does not mean that the entire extracellular fluid is positive or the entire intracellular fluid is negative, because what happens is it's like two magnets in a piece of paper, right? If you put two magnets around a piece of paper, they will actually attract to one another, right? But it stays close to the paper. So what this really means is that the outside of the cell membrane has a positive charge, not the entire extracellular fluid. And the inside of the cell membrane has a negative charge. Good? Okay, so now what we're going to do is figure out how this charge impacts the rate at which the ions are going to move. So now I am at homeostasis, right? Or what we call resting membrane potential. This is the cell at rest. We'll put in the sodium-potassium pump in just a second. And my question is, now that we have these charges, one of those ions speeds up and one of them slows down. Which one speeds up? Sodium will speed up. Explain to me in your words why. Yeah, it's a positively charged going toward the negatively charged intracellular fluid, right? And one of them slows down. Potassium slows down because it's actually positively charged going toward a positive charge, okay? And now that's going to be true for the life of the cell, that sodium is moving slightly faster than potassium because you're not just dealing with concentration gradients, you're dealing with what we call electrochemical gradients, okay? And by the way, there's a whole calculation to figure out how quickly things move. I don't ever teach it because students hate it, but all the other phys professors do.
But still the concentration gradient of the potassium is
It's so massive
so
that it's still going to
much more
move. Yeah. In
faster.
addition, there's also this about potassium. There are more potassium channels than there are sodium channels. So more of them exist in the
But
cell.
it's slightly changed just because positive.
Yeah. Mm-hmm. Okay, so now we figure out how the sodium-potassium pump helps us to maintain this. Because can you immediately see that if you let this go for any length of time, you would lose your concentration gradient for sodium and for potassium. And then, wouldn't you lose your positive-negative nature of the membrane as well? Does that make sense? So the positive-negative nature of the membrane was all due to the unequal leakage of sodium and potassium.
Right.
If I don't continue to replace this, what's going to happen is even though my sodium concentration gradient started out like that, and my potassium started out like that, and sodium started out like that, they're both going to end up like this, right? Given a little time, right? They would just, and if you don't have a concentration gradient, you're not going to have unequal leaking and therefore no charge. Okay, so how does my sodium potassium pump help to maintain this for the life of the cell, or replace it when you screw it up? What it does is it is going to maintain or balance out this leak rate with pumping rate. So it is going to pump what out? Sodium. What in? Potassium. And use 1 ATP each time. Okay, so now can you see why the ratios are what they are?
Yeah.
3 sodiums out, 2 potassiums in for every turn of the pump. Everybody good with that? Okay, so do you have any questions about that? Because now we're about to start to talk about the charged nature of the membrane and how you can fix it and mess with it. Everybody good with that? So you understand how you got those charges? Okay, so if you don't, you are not the only one, so you are welcome to ask. Okay, so go ahead.
So when the potassium flows out and then the inside of the membrane has a negative, why is it negative?
It's because, so remember you started out neutral, right? Neutral on the inside and neutral on the outside, no charge initially, right? And then I moved positive ions out and positive ions in, but I moved them at different rates because of the different concentration gradients. The concentration gradient for potassium was 30 to 1, so it moves out really, really quickly, right? What for sodium it's 15 to 1. So it moves in more slowly, right? So if you start out neutral, and then you have a massive exodus of positives and just a trickle of positives back in, right? You end up revealing that negative charge that was there the whole time. Is that conceptually? Okay. All right, so this is a cell at rest. It's not very restful, is it? So this is the minimum that a cell ever does. All cells in your body have these characteristics. Okay, they're all going to have similar concentration gradients for sodium and potassium, and they're all going to have this positive, negative nature. Do they change it? Of course they do. Do I ever change my blood pressure? Yeah, but I better put it back, right? And so what's going to happen is I'm going to have this as the goal that I always try to replace, okay? So now what we're going to start talking about is this charged nature of the membrane, and then we'll go back and look at it in words in your notes. Okay, so that means that cells have a polarized cell membrane. Does that concept make sense to you? Different on one side than the other? That's what we call it, electrically polarized. Okay, and you can measure how polarized it is. Okay, there actually are teeny tiny little voltmeters. It's a teeny tiny little electrode that you can stuff in the cell membrane and measure how different they are. And so you can measure them, and they tend to measure, most cells average about like this. And the number part of it is not particularly important, but I want you to understand where the negative comes from. So it usually measures at about minus 70 millivolts. So let me show you what the minus comes from, and then the 70 will only matter once you really start to change it. So here's how this works. The voltmeter measures the electrical nature of the extracellular fluid first, because that's what it's going to hit. You guys with me? It's going to hit that first. Uses that as a standard and goes through and measures how electrically different the intracellular fluid is. So can you see why it is negative? So if you use this as your standard and you're measuring how different this is, then that one is negative when compared to the extracellular fluid. Is that okay?
So she's saying it's 70 less.
It's 70 in that direction. Yes, it's 70 more negative. And then we'll change the number, and then the number will make more sense to you when we start messing with it. But do you see why it's negative? Okay, concept check question to see if you can apply that. What would happen to this number, okay, if I stop this for a really long time?
It would
What would happen?
turn to negative, or to neutral.
It would turn to what number? Give me a number. Zero. It would turn to zero, yes, exactly, right? If you can't maintain the concentration gradient, then there's no electrical gradient, and then it goes to zero. Everybody go with that? What would this number be if I was negative on the extracellular fluid and positive on the intracellular fluid? What would you tell me about the number?
So
It would be positive, okay? So that's what we're talking about, right? It's just a way of categorizing and comparing how different the extra and the intracellular fluid are, okay? And they average at about -70, and that's going to be important because we're going to start to mess with it and watch which direction it goes when you do whatever. So this is the polarized nature of the cell membrane. Most of them average at -70. They change a little bit. Some of them are -65, some of them are -75, whatever, close to that. So let's look at your notes, make sure that we can put it together in words, and then we're going to start to mess with this, okay? Millivolts. Millivolts. It's millivolts. Don't let the numbers throw you, because if you're anything like me, you got kind of thrown in physics when they started talking about electricity. Oh my God, I felt so smart in physics when they were doing ballistics. And I was like, all I have to do is imagine pushing something off, and it's just some freaking algebra and trigonometry. I can do this. And then they get in physics and they start talking about electricity. I'm like, I am the dumbest person in this room. But in phys, it's way easier because you can actually sort of imagine or see the ions moving. So it doesn't matter whether it's millivolts or kumquats or elephants, because I'm not going to change the units, right? So you're just going to compare them to themselves. So we'll start talking about that. Okay, so with membrane potentials, just in writing, this is what we just did. We just said that you start out with the ion composition of the ICF with high potassium, low sodium, and negatively charged proteins, right? And we start out with the ECF with high sodium, low potassium, and negative chloride ions, right? That makes sense? And then the cell membrane actually allows for the concentration gradients. And then ions will diffuse down their concentration gradients initially, which will create a resting membrane potential or a charge. So this is sort of the story that we've said. At time 0, the birth of the cell, neutral, neutral, leak channels, you put them in, and then you let them leak. So the cell membrane is leaky, but it leaks at different rates. Potassium leaks out initially due to concentration gradients. Sodium leaks in initially due to concentration gradients. But potassium is faster, and it's faster because of concentration gradient. And then that other thing that I told you, there are actually more potassium channels. So they say that the way that your textbook usually says that is that the cell is more permeable to potassium, right? More permeable to potassium. So if you give that a minute, you become positive on the outside and reveal negatives on the inside. So when you get to this state, this is steady state or resting membrane potential. Your textbook builds this entire thing for you. It's a really, really complicated picture, and I don't use it in class to instruct, but this picture that they have right here, which is 7-8, builds the whole thing like we just did. It starts out with nothing but concentration gradients, adds in leak channels, right? Lets them leak and accomplishes a charge, adds in the pump, and figures out what it does to the number, right? Does that make sense to you guys? So not do you want to look at it in class, but when you are at home and trying to remember how you built the damn thing, that's kind of helpful. Okay, so after resting membrane potential has been accomplished, potassium slows down and sodium speeds up, and it's pretty much like that for the rest of the life of the cell. So the sodium-potassium pump, can you see now that the sodium-potassium pump is not just maintaining this, but also maintaining this? Yeah, the sodium-potassium pump is necessary for concentrations which are necessary for the electrical gradient. And if it wasn't there, you wouldn't have either one of them, or if it gets stopped for long periods of time. Okay, so the last thing to address is, why am I not talking about the negatives? The reason I don't have to talk about the negatives here is because these negatives are impermeable, they're trapped, you don't move them on accident, because they're structural and functional proteins inside the cell. So I'm not saying you can't move a protein, but you're not going to move them in massive amounts enough to cause charge changes, right? And then what about chloride? You get to ignore that one too, because chloride diffuses in the cell down its concentration gradient and out the cell down its electrical gradient at almost the same rate. So it's like water in an isotonic solution. You can kind of ignore it. Does that make sense? So really what you have to do is keep track of the positives here. Are we okay? All right, do you have any questions before I start to change the number and try to figure out how that works? Everybody good? Go ahead. I didn't hear your question.
I'm confused about the little negative sign in the arrow putting in and then how you said it was negative or something.
Okay, so this is measuring the difference between the extracellular fluid and the intracellular fluid. And physically, the way this is actually done is you have a little electrode that measures the electrical nature of the first fluid, which is the extracellular fluid, right? Uses that as the standard and then measures the electrical nature of the second fluid and compares it. So do you see that if you measure the first fluid and then compare the second one, then it's going to be a negative number, right? Okay, so that's what that is. The 70 won't mean anything to you until you start messing with it, but it will eventually. It'll mean something to you. So everybody okay? All right, so now we are going to say every single cell membrane that you have is polarized in a very similar nature to this. Outside is always positive at steady state, and the inside is always negative at steady state. And it averages about minus 70. Don't be at all surprised if it's minus 60 or minus 75, but it's never going to be positive 40 at rest. And it's not going to be 0 either. It's going to be somewhere around there. So now, for those of you who find this a little challenging, figuring out how we got here, this is establishing resting membrane potential. There is a really good review of it in Interactive Physiology, which is either the online content that comes with your textbook, or sometimes you can have it in a CD. I'm not going to test out of it, but for those of you who are very visual and want to see things happen sequentially, that's a good place to go for a review. Okay? All right, so now, this is all with leak channels primarily, right? Just leak channels. So now what happens if I put in a gated channel? Well, conceptually, does it make conceptual sense to you, even though you might not be able to figure out how the number is going to change yet? Does it make conceptual sense to you that if I put in and open a gated ion channel, that number is going to change? Yeah? Because now I have motivation not just for sodium and potassium to move, but for any ion to move. Do you see? Because I've created an electrical gradient. Now any ion will move when given the opportunity. So if I put in a gated channel and open it, ions will move. It will impact the number in a way that you can't predict yet, but you will be able to in 5 minutes. So the number will change. So if you open a gated ion channel, ions will move down their chemical concentration gradient or their electrical gradient, or both.
Is one stronger than the other?
Yeah, that's the Nernst equation. There's a way to calculate which direction things are going to go, and I don't usually make you guys do it, but we can if you want to. So I'll just give you a quick and dirty way that gets you through most of physiology in most situations that you're going to encounter in human physiology. The direction is determined by the concentration gradient, and the speed is impacted by the charge. But of course, you know, there can be exceptions to that. It just works most of the time. Okay, so now together these two forces that cause an ion to move are called the electrochemical gradient. And so now we can get to how these things are related to electricity. Okay, so I have a charged membrane, right? Okay, and if I move charged ions across a charged membrane, that is called a current. Okay. And the body systems that do this massively and purposefully are your electrical systems. Your nervous system and your muscular system start with this charged membrane, and then on purpose they move massive amounts of ions across them, and they create an incredibly large current. Okay, so that's why I think that with physiology, electricity is a little easier to picture, right? Because you can picture a cell membrane. Now you know how it got charged, and now it's not magical electrons that are moving across. Of course, there's magical electrons. It is actually a sodium ion that's moving across, right? So whenever you move charged particles across a charged membrane, you create a current. And then we'll talk about how different magnitudes of currents can be created. Is that okay? Okay, all right. So now the next thing that we're going to talk about is changing this. Okay. Every single cell in your body is similar to this at rest, not just nervous and muscle cells. So this is called resting membrane potential. Neurons and muscle cells use massive changes in this electrical nature to send signals. It is a massive change in this electrical nature of a neuron that causes the release of neurotransmitters. It is a massive change in this electrical signal in muscles that precedes a contraction. So we're going to get to how those happen. But generally, conceptually, I can change this number if I put in an ion channel and open a gated ion channel. Then the number will change in one direction or another. Kind of depends on whether I move positive ions in or negative ions out, and we'll start talking about that. Does it also make conceptual sense to you that you could massively change this number, for instance, in a pathophysiological condition? Like, what if I was completely depleted of potassium and my extracellular potassium concentration goes down massively? Like in a diuretic situation, in which you're like on Lasix, but they're not doing a potassium drip for some reason. Do you see that that would change that number? Maybe you can't predict how, but if you lost extracellular potassium, it's going to change that number, right? Okay, so not surprisingly, when you massively change the electrical nature of a cell, you're going to potentially impact your electrical systems. You're going to impact your heart function, for instance. You're going to impact your brain function. And so the very last part of this set of notes is taking this and applying it to patho situations. So what happens to your electrical systems with losing potassium or losing sodium? But conceptually, do you understand that at least something's going to happen to this number if you lose any of these positive ions or even negative ions on the outside? Okay, so here is what we're going to do. We're going to take this number and we're going to change it. And I'm going to try to lead you guys through how it changes. Okay, so I'm going to give you a couple choices. What I'm going to do is to try to depolarize the cell. So if it's polarized at -70, then depolarize means the inside and the outside become more electrically similar. So what should happen to the number? Goes closer toward zero, exactly, because not polarized at all is 0, okay? So -60, -50, -20, all the way up to 0 is a depolarizing change. Does that make sense to you? Okay, so here's how I'm going to ask you to depolarize. Two choices for depolarizing. Either I'm going to put in and open a sodium channel, or I'm going to put in and open a potassium channel. One of those two will cause depolarization. I want you to sit there and chew on it for a second and come up with your hypothesis as to which one would do it. No, just, I know some people are waiting for me to tell you, but trust me, getting it wrong is way better than not ever thinking about it, right? You'll get it right in the end.
Could you say it again?
Okay, so I want to depolarize the cell, and there are two choices. Put in and open a gated sodium channel on top of this. So the cell never stops doing this, but I'm going to put in and open a gated sodium channel, or I'm going to put in and open a gated potassium channel. I want to know which one would cause depolarization. Got your idea about it?
Yes.
Got it? Okay. All right, so what will do it is putting in and opening a sodium channel. Okay, let's see why. It's nothing magical about sodium at all. It is what I've just set up for the predisposition for sodium. So what's the sodium going to do whenever given the opportunity? It's going to go inside the cell. Okay, so now I started out positive on the outside, negative on the inside. I open a gated sodium channel, and those positives move inside the cell. And now I take positives from the positive outside and put them into the negative inside. And the inside and the outside become more electrically similar. And what happens to the number? It goes up towards 0. Does that make sense? Okay. That is called depolarization. Can you see why sodium is going to be an incredibly dependable ion for depolarization? Because it just works my butt off to make sure I had a strong electrochemical gradient for sodium, right? Now, conceptually, although I won't torture you about this, it doesn't have to be sodium to depolarize. Any positive ion that would move in could depolarize a cell. We will see in cardiac muscle that it's calcium. Or you can plug your ears if you hate this. You can also depolarize by moving a negative ion, can't you? Yeah, you could by moving that. Blah, 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 blah. Am I listening to you? So for right now, for all practical purposes, what I want you to remember is in this figure, when I'm starting at -70, which is resting membrane potential, and I'm going up towards 0, and I can even go past it, and I'll tell you what happens there. This is depolarization towards 0, okay? And that is usually because of doing what to what kind of channels? Opening gated sodium channels. Gated. They have to be gated, right? Opening gated sodium channels, okay? All right, so now the next question will be distinctly easier because you just did that one. So now I want to hyperpolarize. And with hyperpolarizing, it means that this number, the inside and the outside will become more electrically different, okay? So what do you imagine would happen to that number? -70 to where? -80, -90, -100. You guys okay with that? Okay, so they're becoming more electrically different when you compare the inside and the outside. And so I know that you can do it, but I want you to think through it too. I want to hyperpolarize the cell, same choices. Either put in and open a sodium channel or put in and open a potassium channel. Potassium. Okay, so anybody want to explain that to me? Go ahead.
Yeah, so there's already a negative, it's just like we talked about before, there's already a negative charge in there. So if we let all the potassium out,
Yeah, that's it. Yeah.
Then it would further expose the negative.
Right. So what you're doing is you're taking positives from the already relatively negative inside, and you're putting them into the already relatively positive outside, basically amplifying the difference between the two, right? And so you were hyperpolarizing something.
So basically the reason that, so to depolarize that you would add, that you would let sodium in, I mean, it's not because it's sodium, but it's because sodium goes in.
Yes, exactly. It's nothing magical
Potassium
about
goes
sodium.
out, because it's both positive ions, but potassium doesn't go in.
Yes, exactly. It's because, and we set it up so that it would go that way, right? We just worked our little butts off to make it go that way. And you're going to see why in just a second, because I use, in order to send a signal in the nervous system, I'm going to cause a massive influx of sodium. That's how I send signals. And then I have to fix it, and cause a massive efflux of potassium to fix the number. So let's talk about repolarization, and then we'll get back to that. Your question?
So with hyperpolarization or depolarization, what is keeping like leak channels from?
Oh, the leak channels are still going. They're still going. So it's like it will go way depolarized, but if you gave it a minute, it would leak, and that number would change just a little bit. And way hyperpolarized, and it would leak. The leak channels never stop because they're leak channels. They're just leaking, right? So the gated channels are always in addition to what's going on right here. And you can see why I don't draw any more in there, right? Because you're like, you just need to stop right there, okay? So you have to imagine sticking them in there. And I'll show you an animation in just a second. Okay, go ahead.
So now when you say, like, I'm going to put a gated channel here,
Yeah.
like, do they already possess the
Yeah,
gated
so
channel?
this is the whole thing that I was telling you about, me telling you a little fib about everything happening sequentially, because it doesn't, right? You make the damn cell, and it immediately is charged and has leak channels and pumps and gated channels. But we didn't put gated channels in there, so now I want you to imagine sticking one in and opening it.
But they're already there.
Yeah, they're already there. I just like opening a gated channel I didn't draw in there. It's good, but you can see why like trying to like tell the story all in one fell swoop makes it's gobbledygook. You can't figure out how the hell it happened. And that's how my phys professor taught it. He's like, this is the nature of the cell. I was like, what? Why? So I had to like piece it out and tell it a little story. It's a little bit of a fib, but it comes together for a truth. So that's okay, right? So now what I want to ask you is, so conceptually, if I just did a massive depolarization, this one right here, really big depolarization that goes to 0 and it can even flip, go around past 0. First question is, what kind of channel is generally involved here? Be more specific. Gated sodium channel, right? Gated sodium channel. What kind of channel is generally involved here? Gated potassium channel. And now, what if I need to get back to minus 70 really quickly? After I did a massive depolarization, I need to get back to minus 70 really quickly. Any idea how I could accomplish that? Close it, and that will stop depolarization, but it won't do repolarization. So close the sodium channel and then do what? Open all the potassium channels, exactly. So do you see that since it was positives moving in, right? That was sodium, right? Close them, open up a channel that will move positives out, and that's all well and good, and that'll get me back to minus 70, yeah? But the ions are all in the wrong place, right? It's too much sodium on the inside and too much potassium on the outside. How do you fix it? Yeah, you pump your little buns off. That's what you do, right? Yeah, you are going to have to pump it, and the pump just changes the position of the ions, right? And so what we will see is that, like I mentioned, nervous and muscular systems will cause massive electrical changes on purpose, and you have to fix them really quickly so that you can do it again. They are energetically expensive tissues, in part because they have to use so many pumps so frequently. Because if you're constantly messing with your homeostasis, you have to fix it. Constantly messing with your homeostasis, you have to fix it. And the reason they're doing it is because that's how you send signals in your brain, and that's how you cause muscle contraction, but it ain't cheap. It's got a cost associated with it. Everybody okay with that? So what kind of channel doing what is associated here? Not closing the sodium channels happens up here, but it doesn't move it down. What does it do? Opening potassium channels. Yeah, opening gated potassium channels. Good? Okay, go ahead.
So you talked about 4 different types of gated channels.
Mm-hmm.
So what kind of gated channel are they using?
These are usually, the best way to think about them, but not the only way to think about them, is chemical gated channels. So let me just show you, I'll give you a visual on that one, okay? So don't pay attention to the beginning because you haven't learned that yet. But now I'm going to release a chemical. This chemical is acetylcholine, which is a neurotransmitter, okay? And it's going to diffuse and it's going to open these gated channels. These are chemical gated sodium channels, right? Or ligand gated sodium channels. And then when you open those, then sodium is going to rush in, right? Does that make sense? Okay, so the best way to think about those gated channels is that they are chemical gated. Now, conceptually, they could be freaking light gated channels in your eyeballs, but I have no idea how to draw one of those. Do you? Or pressure gated channels, or temperature gated channels, anything but voltage, because we're going to talk about voltage gated channels later. Is that okay? So chemical gated channels is a good place to start, and it's really, really relevant to phys, because of course we talk about chemical messengers all the time. Okay, is that all right? Okay, so depolarization, hyperpolarization, and repolarization. So before we go any further, give me a number that represents depolarization from resting. -20, right? Give me a number that represents hyperpolarization from resting. Yeah, minus 90, minus 80. Okay, so keep that in mind. Okay, so now let's look at the types of changes that actually are going to do this. So the next thing that we're going to talk about is what we call graded potential. So this was resting membrane potential. And now we're going to start changing it, and we're going to put it into the context of a cell that you know. Okay, this is a cell that you know, right? Okay, this is a neuron, and of course we're going to do a whole bunch of this business in a neuron. So the deal is that you can start from resting and then make changes in the electrical nature of the membrane by opening and closing ion channels, right? Okay, and that type of change is called a graded potential, okay? And it's called graded because you can have weak ones and strong ones, and it's called, sometimes it's also called local because it only occurs locally. So I'll tell you what's actually going on here. So you can have a weak one or a strong one. So here's what's going to go on. So remember we just pictured acetylcholine, right? And so what I want you to picture right here, even though they didn't draw them in, is a whole bunch of acetylcholine gated sodium channels. Yeah? Okay. You guys with me? And remember, dendrites and cell body are about receiving information. That's one of the kinds of information they can receive is chemical information. Okay, so acetylcholine. If I have 2 acetylcholine molecules or 10 acetylcholine molecules that open 10 channels, then I will have sodium moving in, right? And the more acetylcholine, the bigger change I get, right? Okay, so what's going to happen is if you record the electrical change at that site right there, you get this magnitude, whatever direction it is, or whatever magnitude it is. But it's depolarizing, right? You see that's depolarizing? But if I move further away from the site of the original channels, then I don't get as massive a change. So if I'm recording it over here at the axon hillock, then I don't actually detect as massive a change. The best metaphor for this that I've come up with is like a pebble in a pond. If you throw a pebble in a pond, then it creates waves, right? But you really are only going to experience the waves if you're very close, right? But if I throw a boulder in a pond, meaning I opened not 10 channels, but 200 channels, right? You're going to feel the effect even further, right? No, we're staying on the same cell. For right now, we're staying on the same cell. If we put in gap junctions, we can go to different cells. So I'm going to feel the change further along the cell membrane, right? But what if I freaking dump a bulldozer in a pond, right? All the way to the other side. So how massive the changes here can have effects on other places in the cell. Now I know you're used to thinking of cells as all being microscopic, and of course most of them are. But remember that neurons have axons. The axon that controls my little toe, its cell body is up here in the lumbar region of my spinal cord, and the axon goes all the way down there. So distance becomes relevant when we start talking about nervous tissue and muscular tissue. And then that axon hillock, what happens there is going to be really important for getting things happening. Okay, so if you cause a small, relatively small change that you can feel more close to the change and less other places, it's called a graded potential. And graded potentials can be strong or weak, right? So this may be 10 molecules of acetylcholine opening channels, and this may be 15, right? They can be strong or weak. They can also be depolarizing or hyperpolarizing. Okay, so let's go back and review for just a second. What kind of channel do you think is opening right here?
Okay. Repolarizing.
That is a gated sodium channel. What kind of channel do you think is opening right here? Gated potassium channel. Got it? Okay, so so they can be depolarizing or hyperpolarizing. And so now I'm just going to make you, I know that you know it, but I'll make you do it anyway because it's part of the learning process. So really all this is having you do is to make sure that you can put the vocabulary together with the concept that you actually know. So on this first figure right here, I want you to sketch the membrane potential recorded in a cell as it begins at rest and undergoes a hyperpolarizing graded potential. Okay, it's not a complex concept. Hyperpolarizing graded potential. Okay, so first thing I need to know is where do I start? I start at -70. Okay, and then show me what I do. Go down. Exactly. So this is a hyperpolarizing graded potential, which is a really long description for a relatively simple concept. And then the other question I can ask you before you leave this concept is what kind of channel doing what is probably involved here? Doing what to it? Open. What kind? Be more specific. Gated potassium channel. Good? And then I know you can do it. We can do it quickly. Let's do the same thing, but this time I want to start at resting membrane potential and undergo a depolarizing graded potential. Where do I start? -70. What do I do? Go up. Same question. What kind of channel doing what's probably involved there? Opening. Gated. Sodium. Okay. You good?
Yeah.
Okay. So now, so let's say we have a whole bunch of whatever stimulus it is, and let's keep it to acetylcholine because we can picture it, right? So now instead of 10 molecules, I'm going to have 10,000 molecules of acetylcholine and a whole bunch of channels that it can open. So if I open a whole bunch of acetylcholine-gated sodium channels, I can cause a massive change in the voltage, right? If you open a whole bunch of them. And so what happens is if you cause a massive change in the voltage, you can start to involve a new type of channel. So here's what I'm doing. I'm going to open a few, and that didn't work. I'm going to open a few more, and that didn't work. And I'm going to open a whole bunch simultaneously. And that will get us to this number. This number is -55. It's called threshold. And what happens at -55 is, let's put it back in the context of this cell. Okay, so here's what's going to go on. I'm going to try to get this cell to -55, but specifically I need the axon hillock to get to -55. That means I'm going to have to even generate a more massive change over on the cell body, right, because it dissipates as you move through. Who cares about the axon hillock and who cares about -55? The deal is that if you cause a massive enough voltage change, you can open a new kind of channel called a voltage-gated channel. And the voltage-gated channel opens in response to a voltage change in the cell membrane. These voltage-gated channels congregated at the axon hillock open at -55 or more depolarized. So you can go past -55, you just have to get to it. Does that make sense? So they open at -55. So here's the story you're going to tell. Massive amounts of acetylcholine get dumped on the cell body over here, right? So I create a huge depolarization on the cell. If it is huge enough, I open the first voltage-gated channel on the axon hillock, right? Okay. It is a voltage-gated sodium channel, is what it is. So here's the story I'm going to tell you. You open the first voltage-gated sodium channel, but I want you to imagine that there are voltage-gated sodium channels lined up along the axon like dominoes. They are close enough that a change in this one will be electrically detected by a change in that one. They're physically and proximity. So here's what happens. If I open the first voltage-gated sodium channel, then more sodium is going to rush in, right? And then my neighbor might not have been quite at minus 55, is probably going to get there, right? And it will open, right? And then my neighbor will open, because they're all set at minus 55. What's going to happen is you're going to hit the first one, and then the first one will make sure that the second one opens, and the second one will make sure the third one opens, until you go adding more sodium every single time.
Into like the cell over there in the stimulus.
Into the axon, the actual axon.
Interesting.
Yeah. So what it's going to look like is maybe I didn't hit minus 55 first, but when I do, look at that massive depolarization that I'm going to get. I'm going to get tons of sodium moving inside the cell. So before I answer your question, what's going to happen is these are lined up all along the axon until you get all the way down to the end of the axon telodendria. You flip that first domino and make sure that the second one goes over and the third one goes over and the fourth one goes over all the way until you get to the end. They're okay? Okay, so this is a phenomenal example of what kind of feedback. Yeah, exactly. So it's sodium that caused the depolarization that opened a sodium channel, which let more sodium in, which caused the depolarization, which opened a sodium channel. And when you do positive feedback, you are trying to not mess around once you start something, right? So this is one of the reasons that electrical signals work so quickly in the body. Once you get that first one started, the fastest axons in your body send a signal 250 miles an hour. Straight down the thing. Okay, you first and then go ahead.
That's what I was going to say. So that's the like electrical impulse traveling down that myelin sheet. Those
Yes.
are.
We haven't talked about myelination yet because that adds a little bit of a tweak to it, but we will in the next 7 minutes. Yeah. But myelination, this is kind of an unmyelinated axon, so we'll talk about myelination.
Is that like what creates the channel? This large amount of
Creates the
current, sorry.
Yes, exactly. Well, yeah, it creates a massive current change, right? Right? So you're causing a massive electrical change down there. And so the reason that those systems that we always talk about are considered electrical systems is because only electrical systems have voltage-gated channels. All systems have the other kind of channels, like chemical gated and that kind of stuff. They can always respond to something and open an ion channel. They can move ions across them. They'll even create little voltage changes. It doesn't really matter, though, because it's not particularly meaningful for them to create voltage changes. But with the nervous and the muscular systems, I have channels that respond to electrical changes, right? So going back to what happens, so if I zap, you guys haven't done the muscle lab where you zap yourself yet, have you? Okay, do that, it's fun, volunteer. It hurts a little bit, but like there's education in it, so fine. You know, you do crap that hurts all the time. It's like interesting enough. Okay, so what happens if you actually put an external electrical stimulus on you, like you actually shock yourself, what happens is it artificially opens those channels. It gets them to minus 55 without the whole first part of it. Like you can cause an electrical change from the outside, which is why if I tell you that muscle cells have to get to about minus 55 in order to force contraction, but now I shock myself, what do my muscles do? They get it there without the chemical stimulus. So they just sort of skip the first part of the whole chemical gated channels and they go straight to the voltage gated channels. Go ahead.
So, sorry, one thing just for clarification. Does each axon hillock have the ability to dump sodium? Or how is, like, how you said there's more sodium produced along the line?
Not produced, but
dumped.
so all along the entire line of the axon, you have those same intra and extracellular concentration and electrical gradients. So
now we're talking about different cells.
no, it's still the same cell, but remember it's a really long cell, right? So, right? Got it? So it's a long, skinny axon protruding from the same cell. So whatever I started down there can continue, right, all the way down the axon. So we haven't moved to another cell yet. In order to move to another cell, you're either going to need a gap junction to stick them together, or you're going to have to start the process
So
all
there's
again.
one cell can run.
It's one long cell. Yes. Does that make sense?
So it's not, I mean, it's not sending a message because it's just sending it itself.
It actually will send a message, but not to it. What will happen at the end, and we'll get to this in the next set of notes, is the whole point of this along the axon. It is the electrical stimulus going from the cell body all the way down the axon to the end, which will cause neurotransmitter release.
The first time I've ever heard of a cell being like
Long, yeah. Yeah, conceptually it's a little difficult to deal with, but yeah, that is one cell, right? One axon that's actually running from the cell body of the lumbar region of my spinal cord all the way to control the muscles of my toe. One cell.
So how does the cell and the nerve, like, are those the same thing, or are they?
No, a nerve is a bundle of axons, right? They're just packaged together for protection. They're packaged in connective tissue. Those are good questions. Go ahead.
So what if this isn't like an axon?
If it's a muscle cell?
Yeah.
Okay, the only place that this happens is in axon, as in neurons and muscle cells. In neurons and muscle cells, basically, you just have this site on the muscle cell that has all of these chemical gated channels, right? And then if you get them depolarized enough, it will open voltage gated channels. It actually goes both directions down in neuron, it only goes one direction down in axon. Go ahead.
So
I'm sorry,
the-
muscle cell.
So the negative 55 doesn't have any relevance in anything that's not in the electrical system?
Yes, exactly. And it's not always negative 55. It's actually different in neurons than it is in cardiac muscle, than it is in skeletal muscle, than it is in smooth muscle. But it's all kind of pretty similar to that. It's always slight, it's always depolarizing, right? It's always around that. So that's just the average.
So
Go
there's
ahead.
no threshold, and does it increase to at least open a cascade or effect?
In other cells?
Yeah.
No, they don't even care about electrical.
Well, so there's never a cascade effect? It'll
No,
just be the same.
Right, it just goes the same, and then you balance it out either by leakage or the sodium potassium pump, and you just go right back to resting. So you don't cause as massive a change in voltage, and you don't respond to it even if you did. So, anybody else? Go ahead.
Just so, like, with the muscle contractions,
Uh-huh.
it's not necessarily just one cell. Is that because of gap junctions? The voltage is transferred?
You can transmit it directly through a gap junction because it's just ions and they can move through gap junctions, but that's only in cardiac and smooth. Skeletal muscle doesn't have it. And we're going to revisit this. Obviously, you can see why we spend time on this because this is relevant to 3 different body systems that we cover in detail. So this is relevant to nervous system, cardiac muscle, which we cover in detail, and skeletal muscle. We don't do a whole hell of a lot about smooth muscle because it's kind of like, and that's kind of like cardiac muscle, but not quite as cool. Okay, so very good questions. So let's put it back in the context of the words of the notes. So sodium will move into the cell down its electrochemical gradient. If you hit threshold, you will open your voltage gated channels, and threshold averages about minus 55 millivolts. Fascinatingly, even though potentially like an action potential could occur with hyperpolarization, we've never found one. Like there are no hyperpolarizing action potentials. There's no reason it couldn't work, right? You could move stuff that way, right? You could move like potassium out and then move sodium right back in to fix it, but we've never actually found one. So all action potentials that we've ever found are depolarizing action potentials. So when you get to threshold stimulus or stronger, you get an action potential. And an action potential is here. So I want to look at this figure real quick, and we're going to pick up on this figure on Tuesday, but I want you guys to see if you can put some things together for me. First question, what kind of channels were involved in getting me to minus 70? Leak, brilliant. Okay, what kind of channels are involved in getting me from minus 70 to minus 55? Be more specific.
Sodium gated.
Chemical gated sodium. Sodium, right? Yeah, it doesn't have to be acetylcholine. Let's all stick with chemicals because we'll all be figuring the same thing. We conceptually know it doesn't have to be chemical, but it can't be voltage, right? Okay, so these are chemical gated sodium channels. Good. And then what gets me from minus 55, sometimes all the way up to plus 30? Voltage gated sodium channels. Yes. Okay, good. You got it? Okay, so now, question I haven't taught you yet, but maybe you can conceptualize and figure out how the hell do I fix it? Obviously, I can't use that neuron again until I put everything back in homeostasis, because if I open channels, sodium wouldn't move in if it's already flooded with sodium, right? I've screwed up my concentration gradients. That make sense? So help me figure out how to get back to minus 70.
So the action potential would send a message.
The action potential sends a message, but I have to fix it or else I can't use it again, right? Because if I left it here, can you think about this? doesn't matter how much more acetylcholine I dumped on that end, it ain't moving, right? Because I screwed up the concentration gradient for sodium. Okay, so how do I fix it? How do I get it back to minus 70? What should I do at the top here? Close sodium. That will stop the whole progression. And then open potassium. Potassium usually slightly overshoots minus 70 just because it moves so quickly. And then it just sort of resets. You don't even really need to do anything for it to reset. This is overshoot. But what? So now the pump is not so much involved in correcting the potassium, but it has to put everything back in the right place. Because do you agree that just because we fix the number, I still can't use the damn cell, can I? Because the sodium and the potassium are in the wrong place. So what am I going to have to do now? Pump, 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 pump. Yes. And where do I need to pump? And this is kind of fascinating. So now I want you to picture this cell, and I'll let you go after one more minute. This cell, one more time, all the way down on the cell body. I have a whole bunch of chemical gated sodium channels, right? And if they get flooded, then I will have a big enough depolarization to open my first voltage-gated sodium channel at the axon hillock, right? And then I'm going to open all of those because those are in series all along the axon, right, all the way to the end. But now, in order to fix it, I also have to have all along the axon so that I can repolarize after I depolarize. I have to have potassium channels, right? And they're voltage-gated, by the way. They just open at a different voltage. They're voltage-gated potassium channels. And then I have to have sodium-potassium pumps all along the thing. So here's what happens, and I'll explain it in more detail next time. So do you agree that it would be great if you could reuse a neuron quickly, right? Okay, so what I'm going to do is a massive depolarization, sodium, 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 okay? But I'm not going to wait until I'm done to do potassium pump, potassium pump. So what I'm going to do is at each site, I'm going to do sodium, close, move over, open potassium, pump, sodium, close, move over, open potassium, pump. So that by the time I get to the end of depolarization, I am almost repolarized, right? So I chase depolarization with repolarization. And we'll pick that up next time. That's where we'll pick that next time.
I think the hardest thing conceptually for me is understanding like the pump. I get the leak and I get the charge that it creates because of the gradient. But I'm just so lost as to what the sodium potassium does.
What it does? Really?
Yeah.
So okay. If this stops, then you will no longer have these concentration gradients. Okay?
Right, but I thought just from the get-go, the only reason that there was a concentration gradient was because that's just how the cell was.
No, actually, so maybe that was my mistake in teaching it that way. So I'm trying to teach you how to use that it's all built. This existed because this.
Oh, okay. I was thinking about it the other way around.
Yes.
Okay.
So this exists because this.
Okay.
Okay?
That makes sense.
Yeah. And then it exists after that to balance it out.
Yeah.
Right?
God.
And then it never gets to stop working. And then you have to work it even harder if you screw up the
Okay. That makes a lot more sense.
Okay, sorry, I didn't mean to confuse you on that one. Hi.
So I had a question after I said that with you about the enzymes.
Uh-huh.
So is there always more substrates than enzymes? Is that why?
No.
No?
No, sometimes there's a bunch of enzymes and not enough substrate. And if that was happening, it would just take a really long time to get up to saturation. If there's a bunch of substrate and plenty of enzyme, if there's a bunch of substrate, then you get up to saturation really quickly. Right. So it just depends on the relative amounts of those kinds of things.
And then I'm still kind of confused about this -70. Is that